Hello. In this video, we shall discuss about spherical lenses. Now, spherical lenses, as the name suggests, they are lenses which are formed or formed out of spheres, or we can say that the lenses form a part of a certain sphere, not just one, but maybe two spheres. And because they involve two surfaces, so they have to be constructed out of two spheres. For example, if I'm taking a lens which is, as we know, is convex over here with both the surfaces bulging outward, then I can say that this surface is a part of a certain sphere which would have continued in that sense, and the other surface is a part of another sphere. Similarly, for a concave lens, we can consider this surface to be a part of one sphere and this surface to be a part of another sphere. In this case, the medium, the transparent medium, lies between the spheres, while in this case, the transparent medium, which is carrying out the process of refraction, that is due to the, we can say, overlapping of these spheres. So, nevertheless, you require two surfaces which have been spherically shaped, and then we can say that they are formed out of two spheres. Now, in each of these cases, we are having both the surfaces to be the same, that is, both the surfaces as concave and both as convex. In this case, both the surfaces are hollow, while in this case, both the surfaces are bulging outward. Now, we can also have various other types of lenses. Suppose we have a plane surface and then that is followed by or preceded by a bulging surface. In that case, this is a plano-convex lens. Similarly, you can have another plane surface which is preceded by a concave surface, or which is followed by a concave surface. So this is now a plano-convex. Doesn't really matter if it is plano-concave. Now, doesn't really matter that whether it is preceded or succeeded by a concave surface. It is always named as plano-concave, and this is always named as plano-convex, whether or not it is preceded or succeeded by a convex surface. The reason I'll tell you shortly. Now, this is therefore these two are double convex and double concave lenses, and similarly, you can have a combination of the convex as well as the concave spheres. That is, if you have somewhat this kind of a shape where you have a convex surface and then you have a concave one. Then we call this as a convexo-concave lens. And if we have an arrangement of this sort, then this is a concavo-convex lens. Now, how do we name these, whether it is convex first or concave first, or why not convexoplane or concavoplane rather than plano-convex or plano-concave? The reason being that the radius of the sphere of which the surface forms a part, if that radius is greater than the other, that name must be considered first. For example, in case of plane surfaces as we know it, plane surfaces, they are a part of a very, very big sphere, we can say. So plane surfaces being a part of very big sphere, incomparable in length, the radius, that case, the plane surface always has an upper hand when it comes to the length of its radius. Obviously, it's not comparable to the radius that we are considering at this moment. So the plane surface will have a greater radius and hence its name will be taken first. Whereas in this case, if you observe, suppose I consider the case of concave or convex. Now the concave surface, if I continue to draw it, that will have a radius somewhat like this. It will be a considerably bigger sphere when we are comparing it to the convex one, which will be relatively smaller as I have drawn it. So this sphere that I have drawn, this sphere is for the concave part, whereas the inner sphere, that is a smaller one with a smaller radius, that is for the convex. Similarly, over here, if I consider the concave part, that will have a smaller radius, while the convex part, that will have a greater radius. So that is why convexo-concave, because convex surface here has a greater radius of curvature as compared to the concave surface. So it all depends on the radius being greater, the name must be considered first, and that is how we are able to know what kind of lens and how will it behave. Now usually over here in our discussion on spherical lenses, we'll be considering double convex and double concave lenses, but we can, however, for numericals and problems sake, we can consider the these kind of lenses as well. So as of now, we'll be just discussing a few terms that are associated with the lenses. Now because we have this, let's take the case of a convex lens. Now in case of a convex lens, suppose this is a sphere and this is a sphere as well, which are the part of which the two surfaces form a part. Then each sphere has a radius, and that radius is the radius of curvature, and it has a center, which is the center of curvature of the given surface, while the point lying almost nearly in between the two surfaces within the lens is termed as the optical center. It is the optical center, and we can imagine an axis passing through it, and that is termed as the optic axis. So optical center, optic axis, and then we have the radius of curvature as well. So this is more or less, it does not really have the pole that was there in case of spherical mirrors, but it certainly has a principal axis which cuts the lens into two equal halves, the upper and the lower halves, and that's the principal axis, again imaginary, but nevertheless all the measurements are made on the principal axis, so you need that for sure. Then next we consider the case of principal focus. Now the principal focus, in case of a convex and a concave lens lies along the principal axis, just like in the case of mirrors, spherical mirrors. So they are the principal axes of both those lenses. Now the case of we'll be considering two principal focus. So over here we have a point on the principal axis where from a light ray if emitted, or a pair of light ray if emitted in a diverging sense, then they are rendered parallelly after refraction. So now they are refracted, and they are refracted parallel to the principal axis and with respect to one another as well. So that is the case of principal focus. This is termed as the first focus in case of the convex lens. Then if we have two rays which were to meet at a certain point on the principal axis, had there been no refraction, they were to meet at this point on the principal axis had there been no refraction, but they are refracted and then rendered parallel with respect to the principal axis. Then the point to which they were approaching is the first focus in case of the concave lens. So in both these cases, the first focus that you are observing, uh, it is that point uh, from which if light rays are emitted in case of convex, or to which the light rays approach in a concave, the light rays get refracted parallelly with respect to the principal axis after refraction. Now we can have other way round. The other case that we may consider is that the same of convex lens. Again, we consider the principal axis and if we have light rays approaching the lens parallel to the principal axis, then after refraction they are converged to a point on the principal axis. Now this point to which they are converged, that is again the principal focus. We call it the second focus. That's why I've named it as f2. But there's no difference in f1 and f2 in terms of the distance from the optic axis, that optic axis or the optical center of the lens. Both those cases, you will have the same distance, that is the focal length in each case is going to be the same. So the focal length, that is the length from the principal, from the optical center of the lens, that is going to be the same in case of the convex lens. And as far as we'll also have the proof of it, because why we are having the same focal length, even if they might be having the different radii of curvature for both the surfaces. We'll have a mathematical proof for that later. Now if I am considering the case with concave lens, then for parallel rays approaching the lens parallel with respect to the principal axis, then they are refracted in a way such that they will meet at a point on the principal axis when produced backward. And this point where they will meet, or they will appear to meet, is the second focus in case of the concave lens. So in all these cases that you see, the definition goes in the similar manner, where in the second focus, if you observe that the light rays are rendered parallel to the principal axis towards the lenses, then they are refracted. One of them meets actually with the principal axis in case of the convex lens, while the other one in case of concave lens, that is produced backward, that gets diverged, so they won't meet on the other side. Here they won't meet on this side, so they have to be produced backward, and they will be meeting at a point on the principal axis, which is the second focus. Again, the focal length in this case is going to be the same for the same concave lens. So the first and the second focus in case of concave as well as convex lens, they will be same with respect to one another, uh, for the same lens considered, of course. And also what we note is that the focus in case of convex is a real one, while the focus in case of a concave lens is a virtual one, because the rays are not actually meeting. They have to be produced in each case to meet at a point on the principal axis. So we have virtual focus in case of concave, while real focus in case of convex lens. Now, as far as the case of convergence and divergence in a lens is concerned, what we can consider is that a convex lens can be taken to be composed of two prisms with the bases of the prisms facing one another and a centrally placed glass slab. So there's a rectangular glass slab in the middle, as you can see, and then you have two prisms on either side with the bases touching the sides of the glass slab. Now, as the prism has a tendency to bend the light ray towards its base, which again we'll be discussing later in case of refraction through prism. And here as well, you'll have the same condition where the prism is bending the light ray towards its base. And as far as the case of refraction through a glass slab is concerned, if the light rays are incident normally, then they won't get refracted and they will be passing straight through. Although the speed changes, but the refraction, because the angle of incidence in that case is zero, so the angle of refraction would be zero as well. Uh, Even if they are obliquely sent in case of the glass slab, which forms the central part of the lens, then well, this is considered to be a glass slab. It's not exactly a glass slab which is present at the center, but the shape that tells us that we can take it as a combination of two prisms with a glass slab at the center. And even if there was an oblique ray which was passing through this so-called glass slab, then what we have learned is that the ray won't get deviated, because in case of refraction through glass slab, if you remember in the previous video that we had discussed, there was a lateral displacement but no deviation, because the light ray incident was emerging parallel to the incident ray, so there won't be any kind of deviation from its path. Rather, there will be a lateral displacement. Now, the lenses that we are considering are thin lenses, and that is why the middle portion as well as the other portions of the lens, be it the prism or the glass slab, they will be completely uh, thin. So with thin glass slabs, the uh, the lateral displacement, which depends on the thickness, that won't be considerably considerably greater, as a result of which you won't really be able to observe any kind of lateral displacement. And that is just for one ray that I'm telling. There will be multiple number of rays that will be entering into the glass slab or the central portion of the lens, and hence you cannot really predict in case of especially monochromatic light source that we'll be considering. So you won't be able to predict the refraction or the lateral displacement. In that case, it won't be that considerable amount. So same goes with the case of concave lens. So in case of a concave lens, you can consider it to be two inverted prisms, as I'll be drawing now. just like that. You'll be considering two inverted prisms and probably a glass slab at the center. And the similar case where the light ray which is incident on the prism is bent towards its base, and for the bottom one as well, you can have the prism which is bending the light ray towards its base, making it a divergent lens. And as far as the central light ray which is passing through the glass slab is concerned, it won't be deviated, and even a bit of lateral displacement, but considerably very low, undetectable in case of thin prisms or thin lenses. So that is the case with refraction and the cases of convergence and divergence. So this is a converging lens, and this is a diverging lens. So cases of convergence and divergence in lenses explained by using this above assumption. Now, having learnt about the refraction through the lenses and the focal lengths involved, we can very well consider the case of lens equations or lens formula that can determine the position of the image with respect to the position of the object, and give us the idea that we had obtained for mirrors. Now we'll be using them and obtaining them for lenses. So again, just like the previous case, where I'll be considering three cases uh, where we'll be using two convex lenses and one concave lens. So three images to be considered in all, three ray diagrams, and then we'll be obtaining the lens equation for each of them, which will be the same, of course. So here's the case of refraction through a convex lens, where we have an object AB, and we have considered the focus. Now the focus is considered on the right hand side, where the light ray which is incident parallelly, that will get refracted through, because the parallel light rays, as you remember, pass through the focus. Now here, even if I've considered the focus over here as well, but the object in this case lies beyond that focal length. So on either side we can consider the focus, but as far as the refraction is concerned, we'll consider the focus on the right hand side, because the object is on the left hand side. We will be usually considering the object on the left hand side of the figure most of the times. So so the light ray which has been rendered parallel from the tip of the object, that is AB, there will be multiple light rays, but we'll be considering two of them. The first one being parallel to the principal axis, which after refraction must pass through the focus, as we have learnt in case of a convex lens. So this passes through the focus. And what about the next one? Well, this is the optical center, where through which we pass the other light ray, and as we have already discussed, the optical center forms the part of the glass slab. And for thin lenses, the glass slab has considerably um, low thickness or very less thickness, and that is why the deviation, which is obviously zero, and the lateral displacement will be very, very, very negligible, and the light ray which is rendered through the optical center passes undeviated and meets the other ray somewhere over here. Now as it meets it over here, spare me for my unclear ray diagram, you can use a ruler or a scale for a better diagram. I'm drawing with free hands. So now you will get an inverted image, because the tip A that was there, that will produce another tip, let's say that's A prime, and obviously the base will be touching the principal axis, and that will be B prime in this case. So we have the object which is having an object distance u from the optical center, and the image with an image distance v, and the focus lying at a focal length small f. So this is the case of image obtained in case of a convex lens when the object is considered to be placed beyond the focal length. So I'll take it as case 1. Now I'll be drawing another case that will be that will have the object to be placed within the focal length of the convex lens. Let's see how it behaves. So I've taken a fresh page for that. So first of all, we have the lens with its optical center and the principal axis passing through that optical center. Once again, I recommend that you use a ruler to draw this. I'm drawing this with my free hands. Now, this is on one side you have the focus, but the focus to be considered is on to the right hand side, which I'll be taking at equal distance as on the left, approximately equal distance. So this object now is within the focal length. One of its light rays which will be taken parallel from the tip into the lens, that after refraction passes through the focus. So that's the refracted ray. The second one is the focus. The first one I think the approximation was not up to the mark, so I will erase that. So that passes through the focus, while the second ray taken from the tip, that passes undeviated through the optical center, and as you can see they won't be meeting, they are diverging. So this ray uh, that has been considered to be passing along the focus, that is the first ray that I had considered, I'll draw that backward, and the other ray backward as well, and they will meet at some point, and this point where they meet is going to be the so that is where the virtual image is formed. We name it as a dash b dash for the object at a b, and you have the object distance now to be equal to u, while the image distance is v, and you have the focal length f at this point, that is f being the focus over there. You have the focal length f. So again, the optical center is at O, and I take this point M parallel to the point A, the line which the light ray which enters into the lens and meets probably the optic axis in that case. So this is the case 2 that we have considered, and now we move over to the third case where we'll be considering a concave lens, the image formation due to it. Now the concave lens, again, as we know, we are considering thin lenses over here. These are highly magnified view. The thickness is not that uh, pronounced. So now you have the optic axis, the principal axis. We take a tentative focal length on either side of same value, same magnitude, and we place, in this case the object can be placed anywhere. The nature of the image will be the same in all the cases. First of all, a light ray which is striking or entering into the lens parallelly, that gets refracted, but refraction has to be in such a way that it will pass through the focus. I draw the diagram the other way around. I start from the focus and then I refract it, so it's easier. That's a hack that you can apply, uh, which is usually applied. So this is the point M which we have been considering so far in all the diagrams. And then you have the other ray to be passing through the optical center undeviated. Now these two points, they meet, these two light rays, which one of them is produced backward while the other is along the optical center. That will give a very diminished image, as you can see. In fact, it's not that clearly visible, so you can see how diminished it is. So now we'll be naming it. We'll be naming these. We'll be giving the same names uh, for derivation to become easy that we had done in the case of mirrors as well. So we have the AB to be the object, A prime, B prime to be the image, and then you have F as the focus. So the focal length here is onto the left hand side, the object distance to the left hand side as well, and the image to the left hand side as well. So in this case, that is the third case, we have all the distances considered on the left hand side. Now we will be taking the sign convention. For that, we'll be moving to the empty space in the previous diagram. Now in this diagram that you see, you have AB as the object, A dash B dash as its image, and then you have the focal length as well, object distance, image distance. The sign convention that we'll be using in this case is pretty similar to the one that we had used in case of the mirror equation. That is the first thing that we can consider as far as the sign convention is concerned. We consider the optical center in each case to be the origin of a coordinate system. Now with the optical center being the origin, you have so this is the first consideration. Now the second consideration is along the principal axis, all the lengths considered will be negative to the left of O, that is the origin of the coordinate system, left of O, and which is optical center in this case, and positive to its right. Similarly, they will be representing the positive and the negative x-axis. Now similarly, above the principal axis, all the lengths considered vertically, all the lengths will be positive, and just like the case of the negative y-axis below the origin, you have all the lengths to be negative below the principal axis, below it. You can either consider the principal axis as the reference point or the optical center as the reference point. In both the cases will be the same. Now as far as the case of equation for the lens is concerned, we have two similarities to consider. Just like, again, I'm repeating it, we are going to use the same conditions that we had used in case of the mirror equation. So the first things first, we have the triangle ABO, and that is going to be similar to triangle A prime B prime O. You can refer to the derivation that we have used for the mirrors, the similarity. Here also you will have the same kind of similarity because you have these two to be vertically opposite angles. They will be the same. These are at right angles, ABO and A dash B dash O. They are at right angles, and being at right angles, with two angles being similar, the third angle has to be similar. So their similarity, they are similar by angle, 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 axiom. So you have A prime B prime over AB to be equal to B prime O over BO. So that's the case with the first similarity. Now, as far as the second similarity goes, you have the triangle. In the rest of the diagrams as well, you can take the same case. That is, you observe ABO and BO, ABO and A prime B prime O is similar in this case as well, and similar in this case as well, because one of the triangles lies within the other triangle, so they have to be similar. And let's get back to the first diagram. Once again, we have the similarity over here of the triangle A dash B dash F, and that will be similar to the triangle here, the point MOF. MOF. Now that's because again we have two vertically opposite angles. You have MO to be at right angles to the principal axis, whereas A dash B dash is at right angles to the principal axis. So they are similar as well. So you have A dash B dash over MO here to be equal to B dash F over OF. Now MO, as you can see, is equal to AB. So you have A dash B dash over AB, which was the case in the first equation as well. Here also you have A dash B dash over AB, and that is equal to B dash F over OF. So we can take this as the first equation. You can take this as the second equation. If you compare the first and second equation, the right hand sides will have to be similar, provided left hand sides are similar. So with the left hand sides of the equations being similar, you have B dash O over BO to be equal to B dash F over OF. Now this third equation that I've obtained, that is going to be common for all the cases that we have considered so far. That is, in these two diagrams as well, you have the same similarity. You have this, you can check for yourself. It will be ideal that you check them by yourself, that these two similarities will lead to the third equation, and it is the third equation where we'll be using the sign convention to obtain the length equation. Well, uh, for me right now, I'll be using the sign convention for this first diagram, the case 1 that is, and I'll leave it to you to try out the other two cases, so that you get to know whether you are doing it correctly or not. So I'll be referring to this diagram, and I'll be using the sign convention over here. So I have a vacant space over here. Let me try this right here itself. So the third equation with the sign conventions will be as follows. So B dash O, this is the third equation that I have over here. So B dash O is, as you know, the image distance in this case, which is to the right hand side, and that will be positive, over BO, it is the object distance, and object is to the left hand side, so the object distance will be, because we are considering these distances along the principal axis, so this will be in negative, and that is equal to, see what I have written over here, along the principal axis, this is the sign convention that we are using over here. The length will be negative to the left of O and positive to the right. So positive to the right means B is positive, and U being to the left is negative, and that is equal to B dash F. Now B dash F is not provided. This is the length that we are concerned, B dash F. Now B dash F, well, that's not given directly, but however you have been provided B dash O, and that minus OF is going to give you B dash F. So that means you are going to have B dash O minus OF is going to be equal to B dash F. As far as OF is concerned, you know that is equal to the focal length. That is going to be positive, in always positive in case of a convex lens, because it is lying to the right hand side of the optical center. Now B dash O, as you know, is equal to V, and OF is F, so V minus F over F. You cross multiply these terms, you have VF to be equal to minus of UV plus of UF. You take the UF to the other side, VF minus UF, or rather I would okay, I'll adjust that, UV, right? We would have preferred keeping UV as positive, the single term. So what do? I divide the entire thing by minus UVF. So dividing this by minus UVF, I divide it right here, UVF negative, UVF negative. So negatives cancel out. Here for the negative, what we have is 1 over minus U remains, and the minus in the second term gets cancelled out. So what do I have is 1 by V minus 1 by U, and here U and V cancel out in both the numerator and denominator terms, and you have 1 over F. So 1 by V minus 1 by U is equal to 1 by F is the lens formula that we were looking for, lens equation, thin lens equation, that is. Now in this case we also can obtain the magnification. As far as the magnification is concerned, I'll use this space because it's only preferable that I consider the space near the diagram. So magnification is, as you know, given by the ratio of the size of the image to that of the object. The size of the image in this case is A dash B dash over the size of the object is AB. But the problem is that it's not completely I over O. It's actually, if you observe this, if this is the definition of magnification, here we have A dash B dash over AB to be equal to minus I over O. Why minus? Because it's lying below. So negative because it's lying below the principal axis, that is the negative y-axis. So that is why we have, as we have A dash B dash over AB in this first equation that we had considered, this one, the first equation had B dash O over BO. So you have B dash O over BO, and this is minus I over O, and that is equal to V over minus U. You can strike out the minus in both those sides, and you have I over O. Now I over O, as per the definition goes, is the magnification. So the magnification is going to be equal to V over U. Instead of minus V over U, which you had obtained for mirror, this will be equal to V over U. So that's it. That's the case of thin lens formula, and the magnification that will be the same for these two as well, which I would like you to try by yourself, so that you can always refer to the case that I have provided in the previous page, and you can go back and forth in the video and you can try yourself. Once you get to do this correctly, then you would know that you have understood this sign convention as well as the equations properly. So till then, thank you for watching.